relationship between two observables, which we just call strong complementarity. So you guys all know this stuff, probably. Hidden variables attempt to explain non-classical physical phenomena by presupposing that the system has certain parameters that are there, but we just don't have access to. And local hidden variable theories say that there's these certain parameters and they occur at each kind of individual space-like locale in the theory. Bell showed that there's actually no local hidden variable model for quantum mechanics by showing that a certain inequality was violated. So this was essentially a numeric proof, saying if you set up this experimental situation with two parties and they try to do something, they get a probability of success that's higher than classically possible. Mermin took this a step further. Well, I think actually G.A. Stead did it, but Mermin said it in a very nice way. By creating this setup where there are actually three parties and they perform various measurements, which I'll explain, and it rules out local hidden variable models not only probabilistically in that they didn't succeed with a higher probability than classically predicted. It rules out LHVs possibilistically, meaning they succeeded at something with some non-zero probability with doing something that a local hidden variable model predicts is impossible. I'm going to talk about that kind of in the context of this program called Categorical Quantum Mechanics. And for the past, I guess, probably 6 years or so, Categorical Quantum Mechanics has all been about developing this toolkit for talking about quantum phenomena. So you've already seen in Ross's talk and in Bob's talk these ideas that we have these dots and you can connect them up and they satisfy different identities and things. This is all developed really abstractly, and it's a very powerful language, so you can prove a lot of things directly in this language without resorting to underlying models. So the idea is, can we use a lot of these tools, a lot of these notions we've developed to do something? And in this case, it's to shed some light on the Mermin argument. So the idea is, can these tools give us a much more structural understanding of why this argument works? So where the flow of information kind of goes wrong, essentially, if we assume local hidden variables. So a crucial part of Mermin's argument is that we don't have deterministic outcomes for all of these measurement setups, but the parity of the outcomes is deterministic. So we have these three lights, and for certain settings of our measurements, we'll always get an odd number of lights, and for certain other settings, we'll always get an even number of lights. Parity is just group sums in Z2. So this is important for strong complementarity. We'll see shortly that there's a relationship between strongly complementary observables over Hilbert space and abelian groups. So in this case, that correspondence is actually a connection between this complementary pair and Z2. So we'll see that that's where the parity comes from. This is basically the outline of what I'm going to talk about. First, just develop a couple of the concepts. So we have graphical notions of complementarity, strong complementarity. We have a classification theorem in Hilbert space. And we have a way to represent measurements in our language as well. So I'll talk a bit about that, and I'll talk about Born vectors, which are essentially just a slightly more abstract notion of a probability distribution. So yeah, I'll talk about what hidden variable models look like in this formalism, and I will talk about the Mermin argument. So complementary observables, an observable, well, it's just a self-adjoint operator. The non-degenerate ones always come with an orthonormal basis of eigenstates measurement outcomes. And complementarity, or what we're calling complementarity, is really just the mug condition. So what was shown by Bob and Ross, I guess probably 3 or 4 years ago now, was that could talk about orthonormal bases using these things called Daggering Frobenius algebras. But you don't really need to know what that is. Well, Ross has already talked about them, but they're essentially spiders. Dagger spiders. And in Hilbert space, well, actually in any category, these spiders come equipped with the notion of classical points. And these are just the points that are copied and deleted by these spiders. And we make one more assumption in that they're transposed. So if you curl around a spider, it just takes it to the adjoint. And under this encoding, you can actually see that there is a purely graphical condition of what unbiasedness means. So this color corresponds to a basis, this color corresponds to a basis, and to say that those two are unbiased is exactly this equation. And this is very easy to see concretely. You can just do the calculation. So when we draw circles, that's the same as the trace of the identity matrix. So it's just the dimension of the space. So dimension times the absolute value of the inner product squared. Do some graphical stuff, and then that equals 1. So, and for all points. And then if you assume that these things are uniquely determined by how they behave on points, so this is the abstract version of saying these points form a basis, then it goes the other way. So it's actually if and only if. So strong complementarity is, well, stronger than that, obviously. So this thing is actually something that's familiar from quantum algebra. This is the antipode condition of a Hopf algebra, which is just a slight generalization of, well, not slight actually, quite a big generalization of group algebras. And to say that two bases are strongly complementary says that they don't satisfy just this one antipode identity, they actually satisfy all of the Hopf algebra identities. And actually, if these things are Frobenius algebras, this one comes for free. So that's strong complementarity. So the question is, how much stronger is strong complementarity than just regular complementarity? And the answer to that is it's a lot stronger. So much stronger that we have a classification result for all dimensions, which would be, you know, we'd all be rich if we had that for normal, mutually unbiased bases. And this is basically the classification result. In F-Hill, all of these things, all of these Hopf algebras are just group algebras. So as soon as I fix an abelian group, all of my gray dots become just a group algebra for that group, and my white dots become the things that kind of complete that as a Hopf algebra. So they're the things that copy the basis of group elements. And then you can complete both of those things as Frobenius algebras just by taking the co-stuff of this, so the things upside down on both sides, to just be the linear adjoint. So that's basically all I need to tell you about complementarity for this argument to go through. And there's a lot of different kind of caveats and things, but we've kind of jumped all the way to the strongest thing we talk about, which is these strong complementary things. But there's also an abstract way we can talk about completely positive maps. And since we're going to talk about measurements and mixed states, we need to talk about CPMs. So, as I'm sure most of you know, if you have a CPM, you can write its Krauss decomposition, just like this. Or we can get rid of the sum by just wrapping all of these little BI's up in a big matrix that's indexed by some basis. This is all finite dimensions. And then we can just do a trace of this, and that turns into that sum. So as we often do, we take a notion from Hilbert space, and we draw a picture of it, and then we take that picture to be the actual definition of that notion. So rather than thinking of this as a higher order thing, when we're in Hilbert spaces, all higher order maps, well, in finite dimensional Hilbert spaces, are just first order maps on S space times its dual space. So we can actually encode our density matrix rho, which was previously in some space A, as just a point in the tensor product A star tensor A. And then just by bending things around a bit, we can actually turn this completely positive map into something that goes from these points to other points like that. So this is really just a topological kind of deformation of the usual concept of CPMs. And this is basically Selinger's CPM construction. So you can start with any particularly nice monoidal category. In this case, it's compact, closed, symmetric monoidal. It also has a dagger. But in particular, you can do this for finite dimensional Hilbert spaces, and you form its category of CPMs living over the top of that category. So the Born rule looks like this, and we can actually express this using the language of CPMs. So the idea is that we can talk about individual probabilities this way, but we can also talk about probability distributions, and we can talk about them just as vectors. So these are vectors that, when written in a certain basis, have all positive entries. And what that basis is this basis of classical points, so this gray basis. And the way we wrap them all up together is we take the outcome of the Born rule for each of these I outcomes and just make it the coefficient for each of these vectors. And then you can see that this thing here, the sum over these three things, is actually just the definition in Hilbert space of this, which is really just a multiplication that's bent around a little bit. So that last this I said was this for people on the other side of the room. And we call any such map defined this way a Born vector. So again, we took something that looked familiar in Hilbert space, we drew a picture of it, and now we take it to be the definition. So we say a measurement of an observable, so a measurement of this gray observable, is just this map. And of course we can do arbitrary measurements by first just rotating our quantum system with some unitary, and then measuring relative to some fixed observable. And we'll focus on two measurements in particular. So the Pauli X. So we'll take the gray map to be corresponding to the X observable. So if we do nothing to the state, and then we measure it, then that's just an X measurement. But if we do a pi on 2 Z rotation to the state, and then measure it, that's measuring the Pauli Y. And since we're going to talk about the Mermin argument, we need to know what a GHZ state looks like. But then a GHZ state is just a perfectly correlated sum of triples with respect to some observable. So once we choose the observable, we know how to write the GHZ state for that observable as just, it's a spider with no legs in and 3 legs out. So we'll take this to be the usual GHZ state, or the GHZ state for the Z observable. So pure states in this CPM construction, we can also write as points by taking the stuff down here and bending it around, and we'll find it a little bit more convenient to actually keep the qubits together, which is why we've done this. So this is the space of the tensor product of 3 density matrices spaces. So this is 3 mixed qubits, but this is the pure state of the GHZ state. So if we measure all 3 of those qubits, we can choose measurement angles for each one, so we can do Z rotations, and then apply these measurements like I defined. And in a fairly neat trick, which just comes from the algebraic structure, we see that our choice of measurement angles is totally non-local. So you can see how this happens. So these are phases, so they're well behaved with respect to this color, and they all just fall out. So all of these minus phases fall out and kind of hang underneath here, and all of these plus phases kind of fall out and hang underneath here. And then this last equation actually just follows from the bialgebra equation. So one consequence of the bialgebra equation is if I have any connected bipartite graph like this, that I can replace it with a graph that has just a single wire here and then that same number of edges up and down. So I mean that's a fairly straightforward derivation. So as you can see, if we permute our choices of angles on each of the qubits, it doesn't affect the overall outcome. So our measurement choices really are a totally global thing. So for instance, we can measure XXX by just not doing any rotation, and then we get a probability distribution that looks like this. So this is something you kind of have to get used to. When we see these two wires here, this is the space of a quantum state. So like a density matrix, when we see these single wires coming out like this is the space that Born vectors live inside. So really this is a probability distribution. And so this is the one we get when we measure XXX, this is the one we get when we measure XYY, for instance. So I'll explain how the Mermin setup works. We have some kind of device, some kind of black box that's firing out 3 particles at a time, and we're going to do 4 separate experiments. I mean, we could do experiments for all the settings, but it turns out these are enough to look at that we can rule out an LHV. So we're going to hypothesize that this kind of setup. So we have 3 boxes. These have settings on them. It's set to X and Y, and a little light bulb will come on. We're going to hypothesize that this admits a local hidden variable model, which means that once this device P fires out its 3 particles, then each of these particles already knows whether it's going to flip the light on, given which setting I put to this switch. So P could be a probabilistic thing that's producing these triples, but once the triples are going out, they're set, they're fixed. And that's what we mean by local hidden variable. And we'll see that we can actually set up a quantum system and its predictions will violate this assumption. So to get this all kind of in the same context, we will phrase it as a global hidden variable model. So we know we can always find a global hidden variable model for any quantum system. All you really have to do is just treat the overall probability distribution as some global hidden variable model. So this is what our global hidden state is. So this is a state of 3 particles, and this state knows which lights it's going to turn on, given each of these 4 global choices of settings. So if this state comes out, and XXX is set, it knows that it's going to turn on the first light, but not turn on the second and third. And the same for the other 4 options of measurement settings. And as you can see, 4 times 3 is 12, so this big state has 12 wires coming out of it. So, as I said, it's always possible to find a global hidden variable model in this sense that will reflect our outcomes. In fact, we can just put our real outcomes for each of these 4 experiments just in a product distribution, and that will certainly agree with our predictions because it is our predictions. But then we can also talk about local hidden states. So a local hidden state is something that once these 3 particles get fired out, all it has to know is for each of the 3 local settings which lights it's going to turn on. So this system knows that if I have set to X, 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 for instance, that it's going to turn on the first light, but not the second 2 lights. And for instance, if it was set to Y, X, Y, or something, then it's not going to turn on the first light, not the second, and it will turn on the third. So that's how we've encoded these local hidden states. And you notice this is a much smaller space. It's only got 6 wires rather than 12 wires. But this smaller space we can actually embed in the space of all of our global hidden states. And the way we do that is with copy operations. So the idea is that, so this thing had XY, 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 and now we can copy its predictions to each of our 4 experiments. So for instance, our first experiment was XXX. So we copied from the first dot, first dot, first dot. XYY, first, second, second. And we can do this for all 4. And we get what I call what someone has called the spaghetti monster picture of a hidden state. So our locality assumption will be something like our global hidden state is actually secretly a local hidden state, and it's sending its outcomes to all of these 4 experiments. So we also need to develop some tools to talk about our probability distributions, and in particular we need to talk about compatibility of 2 slightly different probability distributions. And we do this using invariants. So an invariant of a Born vector is just a comonoid homomorphism. So that means that it gets copied through this many copies of the thing to that many copies. And also it's normalized, which is what this means. If I put in some arbitrary Born vector, it gives me a constant outcome. So these things are basis elements. So having a deterministic outcome after computing this invariant is the same as saying that it's just in a single basis vector. So that's like having a 1 in a single element in this probability distribution. So this condition might have looked a bit complicated, but in Hilbert space, comonoid homomorphisms are just those linear maps which take basis vectors to basis vectors. So in this case, where we go from m copies to n copies, it's just taking elements of the m-fold product basis to elements of the n-fold product basis. So they're just like functions sitting inside of vector space. And when there's only 2 basis vectors, these are just Boolean functions sitting inside of vector space. So we can define a notion of a probability of distribution subsuming or being consistent with another one using these invariants. So we say that for all the invariants on the bigger distribution, this bigger distribution subsumes the smaller one if they agree on all of the invariants of the bigger one. So this idea is like if I have some bit string and I compute some function that's going to give me a constant output for all of the on the entire support of the big distribution, then if the support of the other one is contained in it, it should give me that same constant output. So in a way, it's just a tool for working with these things. And again, this condition looks slightly more complicated, but in Hilbert space, it really just means that the support of this thing is inside the support of that thing. So I mean just the non-zero elements in the column vector. So now we can recast Mermin's assumptions using these 2 more abstract conditions. So locality just means that my global hidden state is actually secretly a local hidden state. Consistency means that my predicted outcomes subsume my hidden state, which means that if some particular outcome is possible, I would have had to have seen it in my experiment. So that's what this assumption, kind of consistency condition means. So Mermin showed that these 2 things were in contradiction. And he didn't use individual outcomes, he used parity. And the way we can deal with parity in this language is we can use the group algebra structure. And this group algebra is encoded in this complementary pair. And the algebra is Z2. So we can compute the parity of these distributions of my actual outcomes just by doing a multiplication. So this is a 3-fold multiplication. So it's just saying, did I get an even or an odd number of lights each time? And as we saw, sorry, it's a little ways back when we computed this thing. Yes, when we computed these things, these probability distributions all looked like this. So it's a consequence just of spider laws that that these things are invariants. So by our consistency assumption, we have to assume that because this gave me a constant outcome on my predicted probabilities, that this will give me a constant outcome. And in particular, if we do a further, so these are our 4 experiments, our control and our 3 variable type experiments. If we then do the overall parity of our variable experiments, then we get 0, 1. So this is the thing Mermin does to start to get toward this contradiction. The point is not what we got. The point is that we got 2 distinct things. So we'll see how this leads to a contradiction. So the other thing we can do is we can apply our locality assumption. So our locality assumption says that if we take this global hidden state and we apply the same thing to it, well, if we take this global hidden state and we replace it with our local form, then for this thing to be consistent, this overall distribution is going to have to be that thing we got on the previous page. And you can actually show, just using diagrammatic identities, that that's not the case. So for instance, if you look at this, I know there's a lot of wires to look through, but there's always a parallel pair of wires connecting from here up to this dot. So these fall away. So as Bob said yesterday, 2 spiders shake 2 hands, their arms fall off. So you actually get something that's symmetric. It's symmetric in its form because this is an abelian group algebra, so it's commutative. So it couldn't possibly be something that looked like that. And that's the Mermin argument. So I think the interesting things about this is you actually really see where the locality comes from. You really get this geometric picture of the fact that I have this hidden state, and my locality says that this hidden state sort of, not really broadcast, but it copies what it's going to predict all these outcomes. So you get this, nice structural, pictorial version of the Mermin argument. So ways we can go from here, which some things we've done, some things we're currently working on, is you can actually form an abstract version of this argument. So you take an n-legged spider, and you get some abelian group G, which corresponds to this strongly complementary pair. And there's always a way you can set up a Mermin-type scenario where this thing will fall apart, and you'll get something that should be symmetric. But then, depending on the category you're in, you'll either get something symmetric equal to something symmetric, in which case you do have a local hidden variable model, or you'll get something symmetric equal to something where symmetry is broken, and you'll not have a local hidden variable. So the idea is to look at this in a lot of different categories. I suppose now it was 2 years ago, maybe 1 year ago, Bill Edwards looked at the Mermin argument in the context of spec, so Rob Speckin's toy category, which is kind of on its face a local hidden variable theory. And in that case, he showed that this phase group of the observable really plays like a crucial role in showing that, for instance, these things will always be symmetric, so you'll always get the same outcomes here. But in quantum mechanics, we have a different phase group which allows these things to be different. So the kind of where we go from here is to really formalize that in this language and talk about a bunch of different situations where we can rule out local invariable models and where we have them. And we can talk about it in different categories, and this could be related as well to axiomatizations of quantum theory and that sort of thing. And yeah, so that's basically what I wanted to say.
Can you show a very quick pictorial proof why this argument doesn't work for 2 parties, why we need 3 parties?
For 2 parties. So I can't show a quick pictorial proof, but the way it works as you try to expand this thing, you can show that your dimension of your space kind of dictates how many parties you get for this kind of setup. So in this case, we have a 2-dimensional space. So we needed to have enough parties here to guarantee that we had pairs of legs here to fall away. Because that had to do with this structure of Z2, that if I have a parallel pair of edges, they'll fall away. More generally, this has to do with what's called the exponent of the group. So if you have an exponent of like n for the group. And if you have n parallel legs, they'll fall away. So what you have to do is you can generalize this by always expanding to enough parties that you get the exponent of the group, or something that the exponent divides of parallel legs, and then you get this symmetry.
Any more questions? Yes.
Kind of a similar question. Do you have a pictorial idea why it doesn't work for the other totally tangent free qubit state, but it does work for the GXZ state?
So you mean why it doesn't work for the W state?
In terms of the diagrams.
Actually, that's a really interesting question. No, I don't have an answer, but so we do have this this graphical theory, this GXZW calculus, which axiomatizes how these two things behave with each other. It's not quite as straightforward as this GXZ calculus, which is basically what I'm talking about with complementary observables. But I suspect there is something that can be said there.
Any more questions? Let's thank Aleks once more.